Okay, so this is about circular motion, and we're going to talk about how we actually describe how things move in circles. Now, you will, last year and at GCSE, have talked about torque, and that is when forces cause a rotation. So, for example, you might have a large force here and a small force there, and we get a torque in this direction, so then we get rotation. Yeah, so that's very, very intimately tied with circular motion. What we're really talking about in this unit, though, is how to describe the way in which things move in circles. Now, that might be something moving in a complete circle, or it might be something moving around an arc. Okay, but that arc, as though it were part of a circle, we can still talk about it having a radius. Okay, so in this case, that arc's radius is this here, even if the road or pathway or whatever continues in straight lines. And you'll encounter this thing quite a lot more often in some subjects, and this, well, I say some units, and this more often some other units. So for this, we could be talking about the rotation of a wheel while you're driving. We could be talking about the rotation of the parts of an engine. We could be talking about a steering wheel. We could be talking about loads and loads of different things, although it's unusual for a steering wheel to move in a complete circle, even though it's a circle itself. Anyway, talk about our terms. We've got the key things we're going to think about in this unit are the radius, which we represent using an R, the length of the arc, which you represent using an S, and the angle in here, which you may remember is represented by theta. Okay, so let's get into what circular motion actually is. So let's imagine we've got something moving in a circle. We'll talk maybe about, okay, here's the Earth, and here is a satellite that is going around it. Okay, so within the questions that we do, we will talk about these things usually having a fixed speed. Okay, so it's an orbit around the Earth with a fixed speed, and of course speed is just distance divided by time. It's the distance covered per unit of time. Okay, but one thing that's very important to remember is that this has a constantly changing direction. So if we talk about the velocity of it, what we're talking about is perhaps its velocity at this point, or maybe at this point, or maybe at this point, or any point along here. So in this case, we might talk about its instantaneous velocity. And that is as though we could freeze time and see what its velocity was at that moment. Of course, things start to break down when we talk about freezing time, because if we did freeze time, it wouldn't be moving anymore. All right, but anyway, if we talk about its instantaneous velocity, at this point, we'll just call that A. What we do to represent that velocity is we will draw an arrow at a tangent to the circle. So bearing in mind that that should be at exactly 90 degrees to the radius. And again, if we wanted at this point or any given point around the circle, all we use is an arrow at a tangent. So this vector here could be used to represent that change of velocity, which would be its acceleration. So we'll get onto acceleration later. Here we're just really describing that kind of movement. Okay, so we've got the speed. Okay, there's three different things we might think about: the speed, the instantaneous velocity, and another property which we call the angular velocity. Okay. Now, when the reason we talk about angular velocity is if you think about in a circle. So let's get away from our example of the satellite in space, and perhaps let's talk about a rotating wheel on a bicycle or a car, just any rotating wheel basically. So if we think about that, we've got our center, we've got our radius. Okay, it could be spokes, it could be just any set of arbitrary points along the radius. Now, at this point we need to think about, according to this, which point is moving the most quickly. And if you think about speed being the change of distance divided by the change of time, then that's got to be at, we'll say, B, at the circumference, because that is where we're getting the largest change of distance for the same unit of time. This is all moving as one line around this, but of course the largest circumference is where the radius is largest. And theoretically at the very center, because we have no distance being changed, there is no speed. Zero distance divided by any unit of time is still going to be zero speed. Now, what does unite this whole thing? Well, let's say this rotates, so this goes the whole way around in 2 seconds. Well, so does this point here. so does point X, so does point Y, so does point Z. They all rotate in that same amount of time, even though they're covering different distances. And that's what circular motion actually is. And this is why it's quite useful that we start talking about angular velocity. So for example, if we're talking about angular velocity, we represent that using this. This is not W, this is a lowercase of the Greek letter omega, which you would have seen before in electricity units. That is the capital omega, this is the lowercase one. So angular velocity, we look at the change of angle divided by the change of time. Okay, and in this case, well, let's just say it does a full circle in 10 seconds. So that means we'll be doing 360 divided by 10, or 36 degrees per second. Fine, simple enough. But what we want to work with instead, rather than using degrees in this case, is we're going to use a different measure of angle, and that is going to be the radian. So let's talk a little bit about radians in this case. I know you've probably already done this stuff in mechanics in AS. We're going to talk about it anyway. Okay, so radians. Now, one thing that you are very often asked, as I've looked at past paper questions, is a definition of radian. That's a horrible circle, but we'll stick with it. Okay. So, the reason we use radians and not degrees, right, is that the radian is very closely tied to the actual shape of the circle, more closely than the degree. Degrees actually emerge, we think, because ancient Babylonians, who were the first to, or who have the kind of earliest math that we talk about mostly, they basically based that 360 degrees on the number of days in a year. I know it's 365, and they knew it was 365, but 360 is much easier to work with because it divides by 2, 3, 4, 5, and 6, and so on. Okay, so it's very easy to work with in that kind of way, especially if you haven't got a calculator, right? So anyway, we're working with radians, and the way we define a radian is if we were able to take the radius and lay it along the circumference of the circle, that would be the angle that is what we call subtended. Okay, that's a word that they use. You don't need to use that. It's the angle that's subtended by the length of the radius along an arc. So again, here we've got theta, here we've got r, here we've got s. Okay, so that means that because a circumference is 2 pi r, that means for a full circumference, or 360 degrees, is equal to 2 pi radians. Okay, which then means that 180 degrees is equal to pi radians. 90 degrees is pi over 2 radians, 45 degrees, pi over 4, and so on. Now, one note on this when you're doing calculations involving radians is if the answer you're looking for at the end is not about a number of radians. Let's say you have to work out an angular velocity or something like this. Keep your numbers in terms of pi the whole time. Okay, I know you could call 2 pi, you could call it 6.283, blah, 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 blah. Okay, but that's an approximation. Okay, so 2 pi is approximately equal to that, but it's not exactly equal to that. So your calculations will be much, much more accurate if you just keep it in terms of pi. So, talking about what radians are, let's talk about how we actually use them in practice. Okay, now you might remember we talked previously about the angular velocity, which, if you remember, we represent using omega. Omega equals the change of angle. Now, we're always going to work in radians when we're doing this. Degrees, we just very seldom use degrees in these kinds of cases. The change of angle divided by the change of the amount of time. Now, you will remember that as we go along the radius, the speed increases. And that means we can actually relate the speed to the radius. I'm going to show you a way of doing that. So, let's look at, for example, okay, speed equals distance divided by time. Now let's consider a full circle of this, okay? So our distance is going to be 1 circumference. So what we can do is we can substitute the distance for 2 pi r if we're going the whole way around. And you'll also remember that in 1 circumference there are 2 pi radians. That means we can now start to relate the speed to the actual angular velocity. So our change of angle, which is going to be 2 pi, the change of angle will be 2 pi if we're doing 1 circle. All right, so that means that we can substitute something from this into this. Let's rearrange this for theta. So I'm going to get rid of the deltas just to make it tidier. So theta equals omega t. So that means we can substitute 2 pi r for omega tr. So omega tr, okay, and then we just divide that by t. So speed equals omega tr, and then of course because we've got this, they just cancel. That means that the speed is equal to the angular speed times by the radius. It's a linear equation. If it weren't, then that would mean that the speeds were increasing. Well, we get larger and larger and larger more quickly as we increase our radius, but they don't, luckily, and the wheels don't fly apart. Maybe in another universe they would, but they don't. Okay? So speed is the angular velocity times by the radius. Again, so that if we were imagining our point at the very center with no radius, then we would have no speed. Okay? So, I think that's everything I want to talk about. That's all the stuff you need to know for what I want you to do today. Try and actually make the meeting next time.